There is a place in the universe where the laws of physics stop working. Not slow down, not bend, stop completely. And the strangest part? We didn't find it in some distant corner of the cosmos. There's one sitting at the center of our own galaxy. It has been there for billions of years, and until about 100 years ago, we had absolutely no idea. Today, we're going to explain black holes. Not the Hollywood version, not the vague, it sucks everything in version. The real version, what they actually are, how they form, what happens if you fall into one, and why physicists lie awake at night thinking about them. All of it explained as simply as possible. Let's start from the beginning. Most people think of a black hole as a giant vacuum cleaner floating in space, sucking up everything around it. That image is wrong. And understanding why it's wrong is actually the first step to understanding what a black hole really is. A black hole is not a thing that pulls. It's a place where gravity has become so extreme that not even light can move fast enough to escape it. Let's slow that down. Gravity, on Earth, is something you feel every second of your life. Drop a ball, it falls. Throw it sideways, it curves back toward the ground. If you throw it fast enough, it could orbit the Earth. And if you throw it at exactly 11.2 kilometers per second, about 25,000 miles per hour, it escapes Earth's gravity entirely and flies off into space. That speed is called escape velocity. Now here's the key idea. Every object in the universe has an escape velocity. The bigger and denser the object, the faster you'd need to go to escape it. The sun's escape velocity is about 617 kilometers per second, much harder to escape than Earth, but still possible in theory. But here's where it gets strange. Imagine squeezing the sun, not changing its mass, just making it smaller and smaller and smaller, compressing it into a tinier and tinier sphere. As you do that, the gravity at its surface gets stronger and stronger. The escape velocity climbs. At some point, you've compressed the sun so much that the escape velocity reaches 299,792 kilometers per second, the speed of light. At that exact moment, nothing, not a rocket, not a radio signal, not a photon of light, can escape. The object has become a black hole. Think about what that actually means. Light is the fastest thing in the universe. Nothing travels faster. And a black hole is simply an object where gravity is strong enough to stop even that, to trap it, to pull it back. So a black hole isn't a vacuum cleaner. It's a region of space where gravity has won completely. And this is where everything breaks down. Because once gravity wins that completely, the normal rules of physics, the equations we use to describe everything else in the universe, they simply stop giving us answers. They return infinities, errors, the mathematical equivalent of a computer crashing. We'll come back to that. In November 1915, Albert Einstein published what many physicists consider the greatest intellectual achievement in human history, the general theory of relativity, a set of equations describing how gravity actually works, not as a force pulling objects together, but as a curvature of space itself. The idea is difficult to picture, but here's a simple version. Imagine a stretched rubber sheet, flat and smooth. Now place a heavy bowling ball in the middle. The sheet sags, it curves. A marble rolling nearby will start curving toward the bowling ball, not because the bowling ball is pulling it, but because it's following the curved surface of the sheet. That's gravity, according to Einstein. Massive objects curve space. Other objects follow those curves. That's why the Earth orbits the sun, why the moon orbits the Earth, and why you don't float off your chair. Within just months of Einstein publishing these equations, a German physicist named Karl Schwarzschild, who was doing calculations from the trenches of World War I while fighting, solved the equations exactly for a single point of mass. And what he found shocked everyone, including Einstein himself. The equations predicted that if you compressed enough mass into a small enough space, something catastrophic happened. Space curved so sharply that it closed in on itself. A point of no return formed. Schwarzschild calculated the exact radius at which this would happen for any given mass. For Earth, that radius is about 9 millimeters. Squeeze all of Earth's mass into a sphere less than a centimeter across, and our planet becomes a black hole. Einstein didn't believe it. He thought it was a mathematical curiosity, a strange solution to his equations that probably didn't exist in reality. He wrote a paper in 1939 arguing that nature would never actually allow such a thing to form. He was wrong, but it would take decades to prove it, and no one expected what came next. Stars are not permanent. Every star you've ever seen in the night sky is in a constant battle between two forces. The first force is gravity, always trying to pull the star inward, collapse it, crush it into nothing. The second force is the energy released by nuclear fusion happening in the star's core, the same process as a hydrogen bomb, but sustained continuously for millions or billions of years. This energy pushes outward, resisting gravity. For most of a star's life, these two forces are in perfect balance. The star just sits there, burning, stable. Our sun has been doing this for about 4.6 billion years, and has roughly another 5 billion left. But here's the problem. Stars run out of fuel. When a massive star, one at least 20 or 25 times the mass of our sun, exhausts its nuclear fuel, the outward pressure stops, and gravity wins instantly, catastrophically. The entire star collapses inward in less than a second. In that fraction of a second, the core is compressed so violently that it triggers one of the most powerful explosions in the universe, a supernova. The outer layers of the star are blasted into space. The light from a single supernova can outshine an entire galaxy of hundreds of billions of stars for weeks. But what's left at the center after the explosion? If the remaining core has more than about 3 times the mass of the sun, nothing can stop the collapse. Not the pressure of electrons pushing against each other, not the repulsion between neutrons, nothing. The core keeps collapsing past the point of a neutron star, past any known state of matter, all the way down to a single point of infinite density. That point is called a singularity, and surrounding it, at the distance where escape velocity equals the speed of light, is the event horizon, the point of no return. The black hole has formed. Now think about what that actually means. A star that may have been 1,000,000 times larger than Earth, one so massive it would dwarf our entire solar system, has collapsed into a point smaller than a single atom. All of that mass, compressed beyond any measure we have words for. And the event horizon? For a black hole formed from a star 25 times the mass of our sun, the event horizon might be about 75 kilometers across, a sphere roughly the size of a small city. But inside that sphere, all of the mass and gravity of a star, 25 times more massive than our sun, is compressed to a single point. If you cross that 75-kilometer boundary, you would be inside a black hole, and there is no coming back. The event horizon is the most important concept in understanding black holes, and it's also one of the most misunderstood. It is not a wall. It is not a surface. You cannot touch it. It has no physical substance whatsoever. It is simply a boundary, a mathematical line in space. On one side, escape is possible. On the other side, it isn't. That's it. And here's the strange part. If you were falling toward a black hole, you would not know the moment you crossed the event horizon. There is no flash of light, no alarm, no sensation. You would cross it without feeling anything different at all. The laws of physics inside the event horizon are not different from outside. Locally, meaning right around you, everything feels normal. You're still falling. Space still looks like space. You can still think, breathe, feel. But here's the nightmare. Once you've crossed, your future has only one direction, toward the singularity. In normal space, you can choose your direction. You can move forward or backward, left or right, up or down. You can also choose to stand still and let time pass. Time always moves forward. That's just how it works. Inside a black hole's event horizon, the singularity is not in a direction. It is in your future. You cannot avoid moving toward it any more than you can avoid tomorrow arriving. No matter which way you point your rocket engines, no matter how hard you thrust, the singularity is where time takes you. It's the only place time leads, and this is where everything breaks down. Imagine falling toward the black hole feet first. As you get closer to the singularity, your feet are slightly closer to it than your head. This means gravity is slightly stronger on your feet than your head. The difference in gravity stretches you, Feet pulled harder than your torso. Torso pulled harder than your head. Scientists call this tidal force. A more colorful name that physicists actually use is spaghettification. You would be stretched into a long, thin strand, like pasta, before you reach the singularity. For a small black hole, this would happen well before you crossed the event horizon. You'd be torn apart long before reaching the point of no return. For a supermassive black hole, one with millions or billions of times the mass of the sun, the event horizon is so large that tidal forces at that boundary are actually quite gentle. You could cross the event horizon of a supermassive black hole without feeling anything unusual at all, which means, somewhere in the universe, there may be objects crossing the event horizon of a supermassive black hole at this exact moment, feeling completely fine, with no way of knowing that their fate is already sealed. Here's something that sounds impossible but has been proven, measured, and confirmed hundreds of times with precise instruments. Gravity slows time, not metaphorically, not as a figure of speech, literally. A clock placed closer to a massive object ticks slower than a clock placed further away. This is one of the core predictions of Einstein's general relativity, and it has been confirmed by GPS satellites, atomic clocks on airplanes, and every other test we've thrown at it. The closer you are to a source of gravity, the slower time passes for you relative to someone further away. Here's a practical example. The GPS satellites orbiting Earth are further from Earth's center than we are on the ground. Because of this, their clocks run slightly faster than ours, about 45 microseconds per day. That doesn't sound like much, but GPS systems need extreme precision. Without correcting for this relativistic time difference, GPS would accumulate an error of about 10 kilometers per day. Your maps would be useless within hours. Every GPS device on the planet corrects for Einstein's equations, constantly, automatically. Now imagine applying this to a black hole. If you were watching a friend fall toward a black hole from a safe distance, you would see something extraordinary. As your friend approached the event horizon, you would see them slow down. Their movements would become more and more sluggish. The light coming from them would shift toward red, stretched out, losing energy, a phenomenon called gravitational redshift. And at the event horizon itself, from your perspective, your friend would appear to freeze completely. Their image would become dimmer and redder, fading almost to nothing, but they would never appear to cross the horizon. Time dilation, gravity's effect on time, would make it seem like they were suspended there, frozen forever. But from your friend's perspective, they feel nothing unusual. They fall through the event horizon in a perfectly finite, normal amount of time, completely unaware that from your view, they've been frozen at the edge for the rest of the universe's history. Two people experiencing the same event with completely different realities. Both correct, both consistent with the laws of physics. Except it doesn't stop there. This time dilation has a strange implication. If you could somehow hover just outside the event horizon of a black hole, not fall in, just stay close, and then fly away back to Earth, you would find that enormous amounts of time had passed on Earth relative to your experience. A few hours near the event horizon could mean years or centuries back home. Black holes are not just destroyers. They are, in a very real sense, time machines. Not all black holes are the same, and the differences between them are almost impossible to wrap your mind around. The smallest confirmed type is called a stellar mass black hole. These form from the collapse of massive stars, the kind we described earlier. They typically range from about 5 to a few dozen times the mass of our Sun. The nearest known stellar mass black hole to Earth is called Gaia BH1, discovered in 2022. It's about 1,560 light-years away. That's roughly 15 quadrillion kilometers, the nearest one we know of, and it's still incomprehensibly far. Then there are intermediate mass black holes, hundreds or thousands of times the mass of the Sun. We've found evidence for some of these, but they're rare and hard to confirm. We're not entirely sure how they form. And then there are the supermassive black holes. These things defy description. At the center of nearly every large galaxy in the universe, including our own Milky Way, sits a supermassive black hole. These range from millions to billions of times the mass of the Sun. The one at the center of our galaxy is called Sagittarius A star. It has a mass of about 4 million suns. Its event horizon is roughly 24 million kilometers across. That's about 17 times the diameter of our Sun. But Sagittarius A star is not even close to the largest known. The black hole at the center of a galaxy, called TON 618, located about 10.4 billion light-years from Earth, has a mass of 66 billion suns. Its event horizon is so large that if you placed it in our solar system, the event horizon would extend beyond the orbit of Pluto. Our entire solar system, every planet, every asteroid, the entire Oort cloud, would fit inside the event horizon with room to spare. And we still don't know how these things form. The leading theory is that they grew from smaller black holes, merging and feeding over billions of years. But the math doesn't always work out. Some supermassive black holes are so large and appear so early in the universe's history that we don't have a good explanation for how they got that big so fast. This is one of the biggest unsolved problems in astrophysics right now. Would you go there, knowing what you know, knowing that if you cross that boundary, that 24 million kilometer sphere of no return, every direction you could point would lead only to the singularity? For most of human history, black holes were theoretical, a mathematical prediction, something the equations said must exist, but that no one had ever directly observed. Then, on April 10th, 2019, that changed. At coordinated press conferences held simultaneously in Washington, D.C., Brussels, Santiago, Shanghai, Taipei, and Tokyo, astronomer Shepard Deuleman and the Event Horizon Telescope collaboration presented an image that made the front page of newspapers around the world. The first direct image of a black hole's event horizon, or more precisely, the shadow it casts against the glowing gas surrounding it. The black hole in the image was not Sagittarius A star, our own galaxy's central black hole. It was the supermassive black hole at the center of a galaxy called Messier 87, located 55 million light-years from Earth. The black hole has a mass of 6.5 billion suns, and in the image, you can see it, a dark circular void surrounded by a bright ring of superheated gas glowing at billions of degrees, twisted by the immense gravity into an asymmetric halo. The image was blurry by the standards of a smartphone camera, but it was one of the hardest photographs ever taken. To capture it, scientists linked radio telescopes across the entire planet, from Antarctica to Hawaii to Spain to Chile, turning the Earth itself into a single telescope the size of our planet. Even then, the data was so enormous that it couldn't be transmitted over the internet. Hard drives were physically flown from each telescope site to a central location to be combined. And what they saw matched Einstein's equations almost perfectly. 100 years after general relativity was published, from the trenches of World War I, Carl Schwarzschild's math held up completely. Then, in 2022, the same collaboration released a second image, this time of Sagittarius A star, the black hole in our own backyard. Capturing it was even harder, because our own galaxy's gas and dust blocks much of the view, and because Sagittarius A star is much smaller and changes brightness rapidly, the team had to process thousands of images and use machine learning algorithms to reconstruct what the event horizon actually looks like. The result was the same: a dark shadow, a bright ring, exactly what Einstein predicted. But here's the thing that the images don't show you. The images are static. They look almost peaceful. They don't capture the reality of what's happening around these objects. The gas swirling at a significant fraction of the speed of light. The magnetic fields twisted into impossible shapes. The radiation pouring outward. The jets of plasma being launched from the poles at nearly the speed of light, stretching for thousands of light years into space. The image is the calm face of something that would be the most violent environment you could possibly imagine. In 1974, a physicist named Stephen Hawking published a result so unexpected, so counterintuitive, that many of his colleagues initially refused to believe it. Black holes evaporate, not quickly, not noticeably, but over time, black holes slowly lose mass and eventually disappear entirely. To understand how, we need to talk briefly about quantum mechanics, the physics of the very small. At the quantum level, empty space is not actually empty. It's filled with pairs of particles that constantly pop into existence and then annihilate each other almost instantly. They appear, they destroy each other, they vanish. This happens everywhere, all the time. Space is a sea of these fleeting quantum fluctuations. Now imagine this happening right at the edge of a black hole's event horizon. A pair of particles appears, one just outside the event horizon, one just inside. In normal space, they would immediately find each other and annihilate. But here, the one inside the event horizon is captured by the black hole before it can recombine. The one outside escapes into space. From outside, it looks like the black hole just emitted a particle. It just radiated something. This radiation is called Hawking radiation, but the energy for that particle had to come from somewhere, and it comes from the black hole itself. Every time this happens, the black hole loses a tiny amount of mass. Over an extraordinarily long time, the black hole shrinks and eventually evaporates completely. How long does this take? For a black hole with the mass of our sun, the evaporation time is about 2 × 10 to the power of 67 years. That's a 2, followed by 67 zeros. The current age of the universe is about 13.8 billion years, a 1 followed by 10 zeros. We are nowhere near the timescale on which this process matters. But here's the unsettling part. Hawking radiation has never been directly detected. The radiation from a stellar mass black hole is so faint, so inconceivably weak, that it's completely lost in the background noise of the universe. We cannot measure it with any instrument we currently have or are likely to build. Hawking's calculation tells us it must exist. The math is solid, but we've never confirmed it experimentally. And this leads to one of the most disturbing problems in all of physics. When a black hole evaporates, what happens to everything that fell into it? The information about every star that collapsed, every particle that crossed the event horizon, every book that somehow ended up falling in, where does it go? Quantum mechanics says information cannot be destroyed. It can be scrambled, transformed, moved, but not erased. But if the black hole evaporates and disappears, that information seems to simply be gone. This is called the black hole information paradox. Hawking spent decades working on it. Some of the smartest physicists alive today argue about it constantly. As of right now, there is no agreed-upon solution. The answer, when we find it, will almost certainly require rewriting some of our most fundamental physics. Either quantum mechanics is wrong, or general relativity is wrong, or both are incomplete in ways we don't yet understand, and no one knows which. Here is a fact that took a long time for astronomers to accept. Right now, at this moment, there is a black hole 4 million times more massive than our sun sitting at the center of the Milky Way, about 26,000 light-years from Earth. It has been there for billions of years. Every star in our galaxy, including our sun, is orbiting it, not being pulled toward it, not falling into it, just orbiting, the way the moon orbits Earth, or the Earth orbits the sun. We are in no danger from Sagittarius A star. It is not consuming our galaxy. It is simply there, massive and quiet, the anchor around which everything rotates. But it wasn't always quiet. There is strong evidence that hundreds of millions of years ago, Sagittarius A star was actively feeding, consuming gas, dust, and possibly stars at a high rate, releasing enormous amounts of energy. During that period, our galaxy's center would have glowed brilliantly with what's called an active galactic nucleus, powered entirely by material spiraling into the black hole, heated to millions of degrees in the process. Some galaxies we observe today still have active central black holes, called quasars. They are the brightest persistent objects in the universe. A single quasar can outshine an entire galaxy of hundreds of billions of stars. All of that energy comes from matter falling into a black hole. Our own galaxy went through a version of that. And the evidence is written in the structure of our galaxy today, in a pair of enormous gamma-ray emitting structures called the Fermi bubbles, discovered in 2010, extending 25,000 light-years above and below the galactic center. The best explanation for them is a massive energy release from Sagittarius A star millions of years ago. The black hole at the center of our galaxy shaped the Milky Way. It may have shaped the conditions that eventually allowed our solar system to form in relative calm, far enough from the center to avoid the chaos. In a strange sense, the most destructive thing in our galaxy may have been one of the conditions that allowed us to exist. We started with a simple question: what is a black hole? And we found something harder to answer. Black holes are not just objects. They are places where our understanding ends, where the equations that describe every other thing in the universe return nonsense, where time and space trade places, where information may cease to exist. Every answer we found pointed to a deeper question we can't yet answer. What happens at the singularity? We don't know. What happens to the information when the black hole evaporates? We don't know. How did the largest black holes form so quickly after the Big Bang? We don't know. There are roughly 100 million black holes in the Milky Way alone, stellar mass black holes scattered throughout the galaxy, invisible, silent, waiting. The nearest one is 1,500 light-years away. There are almost certainly others we haven't found yet. And at the center of every large galaxy in the observable universe, hundreds of billions of galaxies, sits one of these things, ancient and incomprehensible, holding its galaxy together, while quietly evaporating across timescales. The universe itself has barely begun. The universe is not just stranger than we imagined. It's stranger than we may ever fully understand. And somewhere out there, right now, a star is collapsing, and something new is forming in the dark.